Good evening, everyone. And I have one question. You can see. What is this? Okay, that means this is very simple identification for any individual human. Okay, so today we are going to learn something that we can identify some molecule just like a fingerprint. That means that is infrared spectroscopy. Fingerprint means if you look like exactly similar like this, maybe whatever for me, maybe like this, but not 100%. Because as we know that fingerprint means everything, maybe you are coming from same family, your father, your mother, your brother or sister or anyone from same family, you may have same DNA, same structure, same color. However, you have different fingerprint. So we may have different types of molecules like as methanol, ethanol, propanol, pentanol, like this. All of them are from same family. That means alcohol. I am from my family. I have two brothers, one sister, my father, mother, and even I have some other cousins also from my uncle's side or different way. All of them are looking more or less similar, but have the fingerprint which is completely identical for me, different from others, and that would be just whatever we say that if we consider that fingerprint, we can easily identify one person. So if we can understand the fingerprint of any molecule, then we can easily identify what is the molecule. So by using infrared spectroscopy, we can conclude that which molecule is it. So today we will learn the infrared spectroscopy that will give us idea. Initially, we have different regions, but if we see here, you can see two different types of molecules which are very similar in structure. This is one molecule, this is another molecule. Both of these molecules have the structure. You can see this is the oxygen, carbon oxygen double bond. This is carbon oxygen double bond. Here you can see this is carbon and this is oxygen. This is carbon oxygen double bond. This is carbon oxygen double bond. So having both the molecule carbon oxygen double bond, so this molecule gives very similar structure or similar infrared spectrum in this region. That means that is around 1500 to 4000. Within this region, this is one scale. What I'm going to say, this is per centimeter, or we call it wave number. So in this region from 1500 to 4000 wave number, it has very similar pattern in the infrared absorption. That means there is no way that you can tell this molecule is this or this molecule is this. In that case, we have to perform the analysis in some extended region. What is this? In this region. If you can take the infrared spectrum from 500 to 1500 wave number, that is completely different from two different molecules. Even if they are from same group of molecules, this molecule also have carbon oxygen double bond, this also have carbon oxygen double bond, so they are from same family. They are from same family. So actually, to perform the infrared spectroscopy, or what is the purpose of performing infrared spectroscopy? First of all, we will try to find out in which family the molecule belongs to. That means which compound, either alcohol, alkene, alkyne, or aldehyde, ketone, whatever the functional group. So using infrared spectroscopy, first of all, we can understand what types of functional group is present in the molecule. Then, if you have the chance to study, or we have the chance to take the infrared spectra in this region, that means 500 to 1500 wave number, that is very crucial for identifying any molecule. So that would be very much different from one molecule to another. Just here you can see, we have similar carbon oxygen double bond, but you can see this region has the intensity or infrared absorption is quite different from this region. That is completely different, or that would be individual for this molecule. No other molecule in the universe will give exactly similar these types of structure. That is, we call this region is fingerprint region. That would be completely different for one molecule. And in the universe, we have millions of molecules. However, all the molecules have different pattern in the absorption spectrum in this region. You may have something similar in this region, but here you will get completely different, and that will be just like a fingerprint. So if you can perform the infrared spectra for any molecule along this 500 to 1500 wave number, in that case you can identify what is the molecule. Okay, so that is just one basic information or what we are going to learn and what is the importance of learning the infrared spectroscopy. So let's move to the beginning. Yes. Okay. No? Okay. This is the dancing molecule. Dancing molecule, I wanted to show something. What is this? Someone is asking. Professor, did you take attendance? Not yet. I'll take at the end of the class. No problem. Okay. Okay. Still. So I don't know if I can show you the I have one program, a special program, that I will be able to show the vibration. Then how I can show you? Those who are online, they will be able to see, but not you. Come in. Okay, what I'm going to show you. So today we are going to learn the infrared spectroscopy. What I have mentioned that. What is the infrared spectroscopy? In last class, we have learned about the UV visible spectroscopy. Yes?
From the UV spectroscopy, I have a question.
Sure.
So can you explain what is the wavelength of max absorption?
Yes.
Because like,
wavelength max, is it?
yeah,
Okay, lambda max. For any molecule, you will have some absorption region. If you give some energy as light, all the wavelength will not absorbed by the molecule. So if you have the absorption, you will get some spectrum like this. Somewhere it is absorbing very good, and somewhere it will absorb even less. So the position, maybe you are taking the wavelength 200 nanometer to 1000 nanometer. So in certain region, when you are giving a longer wavelength or continuous wavelength, in that case, the molecule will absorb certain portion. So when you go or when you change the diffraction angle, that means the source angle, it will change the wavelength of the light, and the molecule will absorb. So depending on the change in wavelength, where the maximum absorbance we can find out, that is the lambda.
So, Professor, like, if the wavelength is short,
Yes.
so the energy is high.
Yes.
So, would it theoretically absorption be max there?
No, because it has certain types of bond already we have shown you. If you have this type of carbon-carbon double bond, or if you have carbon-carbon single bond, in that case, this is pi bond. So, to excite this pi bond, you need certain amount of energy. To excite sigma bond, you need certain amount of energy. So, depending on what types of bond present in the molecule will absorb that much energy. It will not absorb as much as energy you give. Just how much energy it is required to jump from one step to another, because we know the orbits are quantized, is it?
So, even if we give more energy than is required, it will not absorb.
Yes. Just it will absorb certain amount of energy depending on what is the excitation level, how much energy is required to excite from ground state to excited state or to decompose. If you give huge amount of energy, in that case it can decompose. So that is ultimate one, that means end of the process. But for general purpose, just if you give certain amount of energy, that will excite from ground state to excited state, and that will be determined by what types of bond present in the molecule. Okay. Okay. So now we are going to learn about the infrared spectroscopy. In last class, we have already shown these types of electromagnetic spectrum. So that means for UV spectrum or UV visible, we have this much range. UV and this is visible. So up to this region, that means from 200 or 100 nanometer, around 100 nanometer to 1000 nanometer, or in micrometer, if we could say 100 nanometer, 10 nanometer to 1 micrometer, like this. So that is the UV range. That means we have also shown the energy curve for electromagnetic spectrum. We know that for higher wavelength, that means longer wavelength, the energy is high or low? Low. Okay. So for infrared absorption or infrared ray or infrared wavelength, the wavelength is longer, therefore the energy is short, or frequency also shorter. Okay. So if we give, previously we have given some energy to this region, that means this is quite high energy. So if we give high energy, in that case we can excite from ground state to excited state for the molecule. But if we give even less energy, what will happen? Just we may have some, this is This is one energy level. This is another energy level. So if you give huge amount of energy, so this is maybe considered as ground state, and this is excited. Okay, first excited state. So if you have some molecule from here, you can give some energy in the UV rays, so it can absorb that energy and it can jump to the high excited state. But if you give very less amount of energy, what can happen? It can jump from here to here or here to here. Like this. That means if we give a small amount of energy, in that case, it can absorb very small amount of energy and it can jump. This is our vibrational state. This is our energy level or ground state. This is our excited state, and if all the every energy level has different vibrational level, then every vibrational level has different rotational level. Is it? So if you give lot of energy, in that case, the molecule can jump from this ground state to excited state. But if you have very small amount of energy, that means we are considering this is UV, this is visible. Energetically, this is high energy, this is little bit lower, this is even lower. So if you give this much energy, in that case, we can excite the molecule just from vibrational ground state to vibrational excited state, or ground vibrational level 1 to vibrational level 2, like this. So we will learn infrared spectroscopy is one of the most common and widely used spectroscopy technique employed mainly by inorganic and organic chemists due to its usefulness in determining structure. That means to determine the structure of a molecule, you must need to know what types of functional groups are present in the molecule. For any molecule, if you do not know what types of functional groups, maybe we can consider the molecular formula for this one, C2H6O. Is it? You can write down also like this way. CH3CH2OH. Now, both this molecule, this is structure 1, this is structure 2. Both the molecule has same molecular formula C2H6. Now, in maybe one of the first lectures, I have mentioned about the mass spectrum, mass spectroscopy. In that case, if you take the molecular mass or molecular formula, you can identify using mass spectrum. That means you will get a signal at carbon 12, that means 24 plus 6 plus 16. So how much? 46. Okay. In the mass spectrum, you will have a signal corresponding at 46. For this molecule, for this molecule and this molecule. So there is no way that directly you can confirm the molecule should be like this structure or should be this structure. So if you have the mass spectrum, you can get the idea about this, the molecule, how many ions, or what is the molecular mass of the molecule. In that case, you can guess that this molecule can have the structure either 1 or 2, any one of them. But in addition to mass spectrum, if you can have the infrared spectrum, in that case, you can find out what types of functional groups you have. That means if we can take the infrared spectrum for this molecule, what we are expecting. So if you can take the infrared spectrum, in that case, you will be able to find out in which region we are getting the infrared absorption spectra or signal or intense signal. If you have the signal corresponding to the region where the OH or alcoholic functional group will be found, then if you can find that the signal corresponds to that region, you can confirm that the structure should be this. If you do not observe in that region, we are observing in another region, that is also represented by this type of functional group. That means this molecule should have oxygen or the ether functional group. So if you can take both the analysis, now just using only one infrared spectrum, you can confirm if the molecular structure is this or this. That is also possible if we can use the fingerprint region for the infrared spectroscopy. Because lastly, I have mentioned that for any individual molecule, they have certain region or certain spectrum that will be completely different from others. So if you know the infrared spectrum for this molecule in the 500 to 1500 wave number, that would be completely different from this. So just in the first case I have mentioned, we have to use two different techniques, mass spectrometry and infrared spectrometry, to determine the structure for these two molecules. Either it can be or this can. But if you have the infrared spectrum in the region of fingerprint, then you can easily find out either this one or this one. So in that case, you don't need to have the molecular structure. Sorry, you don't need to have the mass spectrum. So using that, we can easily find out. So this is the technique from which we can analyze the molecular functional group or molecular structure, so that we can identify any molecule. Okay. Now, molecular vibrations. If you have some molecules, the molecule can move, or molecules are composed of different types of atoms. So if we write down here, this is oxygen, this is hydrogen. So if this is a linear molecule or non-linear? Water molecule linear or non-linear? Non-linear. Okay. So linear molecule just like as this. Is it? Okay. So if the molecular configuration is just like a rod, in the just two different ends of a rod, in that case we can consider this is a linear molecule, and if the shape is not in a line, then we can consider this is a non-linear molecule. So if you have certain molecule, you know the pattern, what would be the, just if you can consider what types of the structure is for this molecule, then you can calculate the number of vibrations. What is vibration? If you have this is a ball, this is another ball. So here are three balls we have. If you hold the balls with a spring, in that case, this spring can compress and stress, compress, stress, possible. And if you want to, in one way, you can pull the spring and then it can go other way. If you release the pressure, in that case, the spring can. So that is how, if you consider like this way, this is last day I have mentioned about my head as oxygen and these two hands are hydrogen. So we can move like this way. That is one way. Another way, one time my hand is going far away and this one coming close. Again, like this way, dancing. Okay. Another way, I can go same time, is it? Doing exercise or dancing, whatever you can consider, no problem. So not only this, I can do like this way also, is it? Different way. That means what are the different patterns or what are the different orientations or movement of the atoms in the molecule that are considered as vibrations or molecular vibrations. So how the atoms can move compared to just one atom to another. If we consider this as a spring, that you can easily understand how it can vibrate. So for any molecule, all the atoms are continuously in movement. So you can get the idea how the molecule atoms can move. I wanted to show, I have very good software so that you can easily find out what types of vibration we are showing. I have the, so for any molecule, we can calculate how much number, maximum how many number of modes or vibrational modes can be in a molecule. If you have a molecule like this type, that means if you have a non-linear molecule, in that case, you will have a certain formula. That means here we have 3 atoms. How many atoms and what are the shape? Just you don't need to know the structure perfectly. If you know this is linear or non-linear, that is okay. So what are the number of maximum vibrations or what are different types? We can easily calculate using a formula that is 3n minus 6 and another one is 3n minus 5. So 3n minus 5 degrees of freedom for vibration for linear molecule. So if you have a molecule like this, carbon and oxygen, so you have 3 atoms. That means value of n would be 5. Here also, sorry, value of n will be 3. I think mistake. So here also n equal 3. So what would be the maximum number of vibrations? That can be calculated using, if the molecule is linear, in that case we will have 3n minus 5. So let us calculate 3 into 3 minus 3n minus 5. That means of this one 3n minus 6 equal 3. Okay. So 3 into 3 multiplied minus 6, so that means 3. Okay. So for any water molecule, you can have maximum 3 different types of vibrations. What are they? Just symmetric spacing. This is symmetric. At the same time, it is moving. That means this hydrogen and this hydrogen are going far away or coming close at the same time. This is called symmetric and stressing because it can be stressed and compressed. So this is symmetric spacing. Another one we can have asymmetric or anti-symmetric spacing. That means like this one. Okay. So this is our anti-symmetric spacing. Another one we can have only the bending. So if you go like this way, that is also bending. Is it? So this is our bending. So I have mentioned 3 different types of vibrations. From formula we can find out. Now if I show you the actually what I have from calculation, how many vibrations or what are the vibrations mode, easily I can show you, but if I go to the display, it do not show. That is very so maybe I can rotate my laptop so that you can find it. Just 1 second. Let's calculate the molecule just. This is my water molecule. Can you see? Okay. Now, if I want to show what types of vibration mode we can have, so I am going to show the results. This is vibration. Here you can see 3 vibration modes. 1, 2, 3. Now I will show the types. That means the mouse is not working in this that surface. Oh, that will not help. Because maybe better to use it. Wait, just let me go. Okay. Okay. So just start. If I see, it is dancing, is it? So this is the modes of vibration. One mode. This is bending. What I have shown like this way, and I can say you how much energy it will absorb. I have the number here 1658. 1658 wave number per centimeter, as I have mentioned from the data previously that in the 500 to 1500 wave number. So I have mentioned that if this is not the exact experimental data, this is from calculation, simulation. So always our simulation gives approximate data. So from experiment, we should get within 1500 wave number. So if we consider for a water molecule, it will absorb in the fingerprint region below for this absorption. No other molecule in the universe will absorb exactly like this water molecule. So it will help. That means this is our fingerprint region. And what types of infrared spectra we will find out. I will later show you. So this is our another one. What I have shown. This is dancing in symmetrically. So this is symmetric spacing. So another one I'm going. I've mentioned that the water molecule is a non-linear molecule So it should have maximum 3 vibration modes. Is it? So it should have maximum 3 vibration modes, and from our calculation we also can find out, because we have used the formula 3n-6, and for non-linear molecule we'll have only 3n-6. And if I go for the carbon dioxide molecule, in that case we might have 5 different types of vibrations. Now, what makes the molecule infrared active? That means if we consider all the molecules will give the infrared spectrum, if it is possible or not? Not all the molecules will give the IR spectrum. Some of the molecules will give the IR spectrum and some of will not. Why? Because we have certain, you are familiar with the magnet?
Yes.
You know magnet has different poles. North pole, south pole. Okay. For molecules, we also have something similar like this. That means it says North pole and south pole. You are familiar with the polarity? Okay. So if you have a molecule with the polarity, that means that permanent dipole moment. Dipole means it should have positive pole and negative pole. If the molecule has the positive and negative pole, then we can consider this molecule will have the permanent dipole moment, and that molecule will show the infrared spectrum. So if you have some molecule like this way, that means hydrogen and hydrogen. Do you think that this molecule will be IR active? Do you think? No. Yes? No. We should not. What about this one? It should have. What about this one? Neutral. Yes. In some sense, I would say this is neutral and IR inactive. But sometimes that means if this stressing is not homogeneous, if the stressing or the polarity is not homogeneous, in that case it can show some dipole moment and it can be IR active. What about this one? It should be IR active or inactive? Just you said inactive.
Yeah.
Okay. What is the reason behind this? Okay. In that case, we should not have this water molecule also, because this oxygen has 1 electron, and so it is have 1 electron and it is sharing with another electron on hydrogen. This is sharing and it has, this is completely full. So this is also completely full. That is not the criteria. Yes, you need to think about the polarity, what I have mentioned, that if the atoms in the molecule are partially charged, that means if it has some partial polarity, positive charge or negative charge, whatever. So if we consider for this type of molecule, we may have some, it is not very good way to show this type of molecule as a polar. However, this is very less polar, because if we consider the electronegativity, to know the polarity, if the atom in the bond is polar, you need to know the electronegativity. Is it? For water molecule, for hydrogen, oxygen, and another hydrogen, this oxygen have the electronegativity. How much? Do you know the value? 3.5. And hydrogen has the electronegativity 2.1. This is 2.1. So if you have a molecule or when this types of bond is formed, this is water molecule, is it? So water molecule is forming when this oxygen atom and this hydrogen atom, this here we also have another hydrogen atom. So it is sharing one electron. This is one electron with this, and this has another 4 electrons, and this has 1 electron, like this. Is it? So we know that the one thing is formed in between when this oxygen atom and hydrogen atom, they are sharing the electron, 1 electron, to make the covalent bond. Okay, you are familiar with this type of covalent bond. When the hydrogen atom and oxygen atom sharing 1 electron, they are making the covalent bond. But if their shared electron are not equally shared, not equally, that means this oxygen has the tendency to take the electron towards itself more compared to this hydrogen. Because I have mentioned the electronegativity value for oxygen is 3.5, while for hydrogen is 2.1. So in this bond, the shared electron do not exist like this way, not in middle. The shared electron do not remain at the center of the molecule or at the center of the bond. Then where it exists? Closer to the. Therefore, it do not have electron apparently. That means it is no electron apparently. Therefore, we can consider partial positive charge. Is it? That means deficiency of electron for this hydrogen. And here we have 1 extra electron in addition to number of protons. Because this oxygen has 8 protons. Now, if this electron comes from the hydrogen, that means it has 9 electrons in addition to 8 protons. Therefore, it should have partial negative charge. Okay. So now you can see here 1 pole, this is another pole. Positive pole, negative pole, like a magnet. Okay. Just this is 1 pole, this is another pole. Therefore, we call this is a dipolar molecule or polar molecule. Okay. Water is a polar molecule. How? Because we are having some partial positive charge and partial negative charge in the molecule. Therefore, this is a polar molecule, and if you have any molecule like this, the polar, in that case, these molecules are IR active. And if it do not have any, if the molecule do not have the polarity, in that case, it will not be IR active. Because IR activity means IR activity means IR is we are giving some electromagnetic radiation, just like as energy. Is it electromagnetic radiation or kind of energy we are giving to the molecule? That means this is kind of electric field. So if you bring 2 magnets, if one magnet, just maybe if I consider this is north pole, this is north pole. So if you bring 2 north poles, then they will repel. So if you bring one south pole and another north pole, then they will attract each other. That means, therefore, I am considering this is my external field, this is my internal field or molecule. So if the molecule has dipole moment, in that case, we have some possibility that we can deflect or we can change the orientation or we can change the molecule by using external field. That means by using infrared light. So if you give some infrared light to the molecule, if the molecule has a permanent dipole moment, it can change the orientation or it can change the modes of vibration. Therefore, if you have the dipole moment in the molecule, in that case, the molecule can be infrared active or it will absorb the IR light. Okay. Already I have answered that. How many vibration modes are there in the linear carbon dioxide molecule? Already I have calculated. Now, how many vibration modes for methane molecule? I have the question here. Just you can easily calculate using the formula. CH for molecule. Already I have the answer, but you need to calculate. If this is linear molecule, Cn minus 5. Okay, Cn minus 5. C into N is not how many? 10. So it should be how many vibrational modes are there in tetrahedral CH4 molecule? What I have told you about that. For linear molecule, that should be 3n minus 5 because I have written this is for linear and this is for non-linear because water molecule non-linear. So 3n minus 6 that should be this is the answer. So for any molecule, if you are familiar with the formula or if you know the shape, then you can easily calculate how many different types of modes of vibration it will have. So if I show you the methane molecule, I can calculate the methane molecule vibrational modes. Maybe it will take around 1 or 2 minutes. So I can show you we have maximum 9 different types of vibration modes. So I don't know, I'm not going to show you that one because already I have shown one. So let's move for the instrumentation. That means in last class we have learned about the UV visible instrument. Now we are planning to learn how the IR instrument works. Most of the things are very similar what I have mentioned in the last class. That means we had a light source. In the last class, we have UV light source or visible light source. Is it? So here we have a IR light source. That means with very low energy. IR means the energy which is very low compared to the visible or UV. So we have to have a light source which can generate the infrared light. Normally we represent using like this way because IR has no, we cannot see by our eye. So just we can show like this way. This is our light source. Now we have a monochromatic system. That means this is our light and we can separate. We can separate the light in 2 different angles, sorry, 2 different parts. Last class I have mentioned as splitter or half mirror. Half mirror, can you remember? That means what is the half mirror? Just if we have a mirror here that can separate the light just 50-50. That is half mirror. So something like this. So we are just using some arrow. That means 45-degree angle. 50% going this way, 50% going this way. Okay. Now this is our mirror. This is another mirror, but not all types of mirror are effective here. For IR light, we have specific types of mirror. We use normally gold mirror, just made of glass and then coated with gold. How much expensive that should be? Actually, that is not so expensive compared to several other optics. because just we are giving very thin layer over the mirror. So that is for IR light, you need to use some gold mirror. That means it can reflect most of the IR light. So now, if you pass some light, this is our sample, and this is our reference. That means last class we have mentioned for reference and sample, we have different two cells. So if you have a sample, so some molecule, that means like water or something like this, which can absorb the IR light. So depending on what types of vibration. So if the molecule have some vibration, I have mentioned for water, it can absorb only 3 different types of vibrations. And if you give continuous wavelength for the IR, only 3 wavelengths will be absorbed by the water molecule. What are they? I have mentioned one of them, just that was around 1658 something or 1600 plus. That is for the bending. So what I have mentioned like this way, this is our bending vibration for water molecule. So actually I didn't mention one thing, why the molecule will absorb the light. That is very important. Now you are familiar with the interference of light. Have you ever heard? Resonance. Okay, so you are familiar with the resonance and also maybe interference of light. If these are two wavelengths, now if their phase, that means if their shape and the amplitude, everything are same, in that case it can have the amplitude. That means if we sum up these two lights, is it? If we sum up these two lights or these two wavelengths, in that case we'll have like this. Okay, so at the maximum point, the intensity of the light will be very high. So in that case, any molecule, I have mentioned all the molecules are continuously vibrating. Okay, that means if the molecules continuously vibrates, so it has some like this way, or we can consider some wave like this. The molecule is continuously vibrating, so we can consider something wave like this. Now if you give some IR light and you are changing the wavelength continuously, that means you are generating light from the source, you are giving from this source, and if your molecule is continuously vibrating, now you are changing the light wavelength. If the energy of the light, and that means we are giving different wavelength or different energy. That means sometimes we are giving light with very high wavelength, sometimes we are giving very short wavelength. So when the light of this source matches with this energy, that means this is our molecule. This is our the wavelength from the molecule, what we are getting from the vibration. Now, if we give some if we give some light from the source that exactly corresponds to this wave, in that case, what will happen? Yes, that will be the absorbance or resonance, because already I have shown if you have two waves with same phase and same shape or same wavelength, that two lights can at the same time If they can overlap, then they can have the resonance. Therefore, if we have the light source match exactly with the vibration of the molecule, only that region the IR light will be absorbed. So we are changing the wavelength and the molecule will absorb the light. Just when the modes of vibration for the molecule will match with the light energy. That means light energy means what the wavelength we are giving. So if our molecule is continuously vibrating at 1500 per centimeter, let us consider this is the energy of this water molecule bending. This is one mode of vibration. Another, if we consider like this way, this is symmetric spacing, that will be around 3600 per centimeter, and anti-symmetric, that would be around 3750 per centimeter, like this. So you are giving different energy from the source, and if the water molecule is continuously vibrating, only these three different types of modes. Sometimes it is bending, and sometimes symmetric spacing, anti-symmetric spacing, like this. So if the light source have the energy just like this way, this mass the water molecule will absorb. So if you give the molecule, here is our sample. Now we are getting the light from this. We are collecting the light after the absorbent. If the molecule absorbs some light, in that case, we will have the intensity of the light little bit reduced. Because here we have another portion. Because here 50%, here another 50%. So if this is our reference, so it should not absorb at all. Okay? So it should not absorb at all, it should absorb something. If it absorbs something, therefore this is our reference. Reference means how much light we should have if there is no sample here. That is our reference, is it? So if there is no sample here, we should have the exact light intensity. What we are getting here, there should be the same. But if the sample absorbs some light, that means where the absorption matches the frequency, is it? So in that region, the molecule inside the sample sample chamber or the cuvette, it will absorb some light. Therefore, this side we are getting no change of the intensity because this is reference, it will not absorb the light. Or if it contains water, or if it contains methanol, let us consider, or here also methanol. This is our two solvents, therefore same solvent. So if we do not have any other molecules except the methanol, in that case, if we have the 20% absorbance, here we will have also 20% absorbance. Now, if you have this molecule, here we have some sample. So if it absorbs some light, in that case, if the intensity of this light will reduce because this is, we are measuring the light intensity, that is how much light it is passing through. So if it absorbs something, in that case, the intensity for this light will be reduced, maybe around 15%, let us consider. So we should have 20%, now we are having 15%. So some of the light is absorbed by the molecule. So that is the how much light we are absorbing by this molecule, and if you change the wavelength continuously, so normally Normally, it should not absorb the light until we reach these three different wavelengths or wave number. So, normally, what types of spectrum we should have? We are detecting both the light at the same time. This one and this one. Okay. So, this, whatever the intensity, let us consider this is 400 per centimeter, and this is 4000 per centimeter. Okay, so if you increase the wavelength from this source, or you change the wavelength, and you have the water molecule inside. In that case, you are expecting to absorb only these three wavelengths. We have the possibility we can change the wave number. Actually, I should not say the wavelength. This is wave number in frequency. So, if we change the frequency from 400 to 4000, if the molecule, if the water molecule inside, it should not absorb any light. In that case, the reference and the sample should have the same intensity. Is it? In that case, let us consider this is our 100% transmittance. So we can consider that from here we are starting maybe around whatever going through this, we are getting exactly the same. Now, at certain point, where the water molecule absorbs, you will have that the intensity of this light decreases because it is absorbing some of the lights. Therefore, you can consider the light intensity going this way will be reduced a little bit. Therefore, we can consider that the absorption intensity or the light intensity will be decreased. So, where the absorption matches this one. If our wavelength matches to this, that means that is the bending vibration of water molecule. So, at this position, the water molecule will absorb the light. Therefore, in that case, our this transmittance will be little bit less. That means from here you can see that the transmittance has been decreased little bit. Okay. So, in that case, then once we cross the region, that means already cross the 1500 wave number. If we cross this region, maybe around plus minus 50 wave number like this. So you can consider this is 1450. This is 1550 like this. So when it crosses this region, again exactly the same intensity for this one and this one, because water molecule is not absorbing the air at all. Therefore, we will have the same intensity for reference and the sample. Now, when it approaches this number, that will have the possibility to absorb, so it can absorb little bit. Again, here maybe the range can be plus minus 20, something like this, because that will depend on another types of calculation. Maybe later I will show you. So here we will have some possibility to absorb the light. Now, just when it crosses this region, again it will have the sample and the reference exactly same, the intensity. When it approaches from this one, we will have again little bit change, and that is the. So, if you have the infrared spectrum for water molecule, you should have these types of spectrum in the infrared absorption band, and this region, 500 I can consider, This region is the fingerprint region, and this region is the just common or just family. What types of functional group it has? Water molecule, so it has OH functional group, is it? So we can consider for the water molecule, for this is symmetric OH, this is anti-symmetric OH. So for water molecule, you will have the 3 different types of vibrations, and in the IR absorption region, we will have 3 different vibrational modes, and it will absorb the IR light only in 3 different positions. So this is the instrument what we are getting. So here we are getting the detector, how much light is transmitting through this, and this is the from the reference. So if the sample do not absorb the light, in that case, the intensity for this light and intensity for this light will be same. When it absorbs the light, then the intensity for this light will reduce. So we will get this types of peak, and that goes down. Yes.
This reference is not changing, so it should be a straight line always.
Okay. Yes.
Without here, it's not straight. The yellow color.
Oh, okay. This is that one. Okay. That is actually, I would say that should not be like that way, because 100% absorbance or the light source, what we consider, if we change the wavelength, that the light intensity do not remain the same most of the time. That maybe it is a little bit confusing what I'm saying, but in general, I would say it should be flat. What it is showing, it is not perfect. In general, what I'm showing or what I'm telling, it should be exactly flat. What I have shown like this one. Okay. In general, it should be. But I think the display what is showing, this is not the exact one what I am going to tell you. So please consider that if the IR light is not absorbed by the molecule, we would expect the flat line. But actually, all the instruments have some limitations, and in that case, we have some noise. So in that case, we may have certain little up and down, but here we may have some like this way. Okay, maybe not exactly flat like this up and down, but if the quality of the instrument is good, in that case, this line should be quite flat or quite straight. But that is not very necessary, because for these types of vibration, if you want to detect what types of vibration you have, if you have something like this, still you can identify this one, is it? That is fine. But nowadays we can have very good quality infrared spectrometer, so that we can have very flat line, and we can very clear as much as the signal to noise ratio. Are you familiar with this word? Signal to noise ratio or SN ratio. Okay, that is called like this, SN ratio. Okay, signal to noise ratio. So that is for any instrument, if the signal intensity is very high compared to the noise, this is our noise, what I have mentioned. So if this is not our interest, but all the instrument has some noise, that means the signal is not corresponding to any our expectation, and the molecule or the instrument, due to some electrical defect, it can have some increase in the signal. That is the noise. Therefore, if you have the noise is very high and comparable with the signal, that types of instrument is very bad quality. That means if our noise is like this or maybe like this, then it is very difficult which one is our expected signal and which is the noise. Therefore, we should avoid that types of instrument. So people are trying to develop the instrument in such a way that we can have very flat line for the noise, and as much as we can increase the signal that can be very good quality. So this is the signal to noise ratio. That means if the ratio of the signal and noise is very high, the instrument quality is very good. Because if you consider this is 100 and this is maybe 2, in that case 100 by 2 is 50. If you have this 100 and this is 10, this is maybe 10, that will give you 100 by 10. So SN ratio becomes 10. So this one is better compared to this SN ratio, signal to noise ratio. If the instrument has very good signal to noise ratio, then your instrument is good. And if you have other way, the instrument is quite bad. Okay, so already I have mentioned that type. IR includes radiation with wavelengths between 2.5 micrometer to 25 micrometer. Whatever. Already we know X-ray is very high energy. In last class we have mentioned that if we give some X-ray, that is very high energy. Therefore, we should already mentioned that we should not have the X-ray very often. So that is very high energy. It can penetrate through our body, even skin, and also through the bones. So that is very high energy. But normally IR or visible light that cannot penetrate through our body or in the bones. So ultraviolet visible, it can excite the molecule from one electronic state to the another electronic state. That is energy little bit lower than, not little bit, quite lower than X-ray. Then infrared, that already I have mentioned that we can excite the molecules from one vibrational state to the another vibrational state, not in the electronic state. Just electronic state, to excite the molecule, we need to have UV or visible light. That is quite high energy compared to IR. Then microwave, radio wave, already mentioned about that. In terms of wave numbers, okay, for different types of functional groups, what types of functional group we have? Based on types of functional group, we can have the IR absorption in different regions. Because already I have mentioned that if I show you here that OH is close to 4,000 and CH that is around 3,000. 3,000 wave number, which is around 3,600 wave number. So based on what types of molecule and what is the dipole moment of this bond. This is OH. So oxygen and hydrogen, they have polarity. Therefore, they can have, and depending on their mass also. Later we will show the equation, maybe. Okay, this is our bond as spinning like this. Maybe I go for this one. So Hooke's law, you are familiar with the Hooke's law. So Hooke's law says that the vibration frequency of vibration is mu equal k square root of f divided by m. Then what is the terms individually? F is the force constant. F is the force constant. It's a little bit difficult to see because the quality of the display and even the color may be not very good choice. So here F is the force constant and M is the mass of the molecule. So frequency mu equal k, this is a constant, square root of F divided by M. That means if actually this comes from this equation, mu equal 1 by 2 pi c square root of F divided by micro. So this is what we call it reduced mass. Are you familiar with the reduced mass word? This is the formula. If you have two objects, then the objects with mass m1 and m2, then we can find out the reduced mass by this equation m1 m2 divided by m1 plus m2. So just we can consider that that is related to the mass. What we are going to show in the next slide. So this is m. So if you have two molecules with very high attractions, that means very large dipole moment. In that case, you can have that the frequency is very high, because if you write down the equation, frequency is proportional to a square root of f. We can write down like this, right? This is our formula, and frequency is inversely proportional to a square root of n. 1 by n. Is it like this? That means if the mass of the molecule are smaller, in that case the absorption frequency will be very high. And if the force constant, that means if their attraction force is very high, in that case the frequency will be high. Therefore, we can consider for oxygen. So in the previous slide, what already? Okay, no problem. So this oxygen and hydrogen, they have very high attraction force, because due to have very electronic configuration, or just we say that very high dipole moment. Is it? So they have very high attraction force or force constant. Therefore, the absorption frequency for this molecule or this OH, it should be high. And if the mass is very large, in that case, it should absorb for larger mass. That means less frequency. In that case, see here, carbon nitrogen or carbon halogen. If you consider carbon halogen, this is very heavy molecule. So therefore, it is absorbing the lower frequency. This is 400, 1500, 2000, 2500, 4000. So just using this formula, we can consider, or we can have idea where the absorption frequency for the iron light for any dipole molecule or dipolar molecule will be. So here we can consider, or you know this formula, so you can guess in which region it should be. That means for any heavier molecule, the absorption frequency will be low, and for the molecule with heavy attractions or very large force constant, we will have the attraction force high, and therefore the absorption frequency will be very large. That means very large absorption frequency means you need very high energy. That means compared to here, if you consider this energy and this energy, 400 and 4000, that means the energy for this 400 wave number is very low. This is compared to, that means at least 10 times more. 400 to 4000. So this high energy, this is low energy. So if you have the force constant is very high, in that case you can expect that the absorption will be around 2500 to 4000, or even close to 3000 or 4000. That is, so for any molecule we can guess where the absorption frequency will be using this formula. We have the data carbon hydrogen. So this hydrogen is very small atom, is it? Therefore it has very small mass. Therefore we can consider that the absorption frequency will be very high. Oxygen, hydrogen, this hydrogen also very small. Therefore we can consider that we will absorb, even it has very high attraction force. Therefore overall we can have that the absorption frequency will be quite high. Okay, here already I have mentioned for fingerprint, ray sensing, the IR spectrum, the detection of different bonds, a strong peak. Okay, if you have a strong peak is tall, transmittance is low, 0 to 35%. Here, if you consider, this is our, what is this? This is transmittance. How much light is transmit? So transmittance, this one. So this is our absorbance. How much it is absorbing is corresponding. Therefore, opposite of the absorbance, it should be transmittance. So, if do not absorb at all, in that case, we will have close to, actually this is our 100%. So, it is absorbing. As we have previously shown that some of the, someone have mentioned that the line is not flat. So, from experiment, we are getting like this one. Actually, we are expecting that here no light is absorbed, no IR light is absorbed. But still, we can have some absorbance because here we do not have the absorption or we do not have any vibration. However, still we are having some absorbance. So we should have the transmittance 100% in this region because it do not have. However, it is quite clear that we can have different types of vibration modes. We can easily assign what types of modes we have here for any molecule because this is our baseline. Are you familiar with the word baseline? Baseline? Okay. So baseline, that means where it is very similar to the axis. Is it? So it is parallel to the axis. We can consider just it should be. So here we can consider this is our baseline. This is also our baseline. So we should not have any absorbance in this region. However, due to our different types of problem in our instrument, we can have some noise or always we can have some limitations or we can have some signal which is not expected or which is not coming from the sample. However, if the molecule have certain absorbance, then we can easily find out where we should not consider this is a noise. Definitely. The signal intensity is quite low, however, not like this one, not like this flat. Therefore, we can easily consider this is the signal coming from something, some modes of vibration. Therefore, and already we have mentioned about the fingerprint that only this region, if you can take the infrared spectrum in the region 500 to 1500, we can identify any molecule without any other types of any experiment. You don't need to take the NMR, you don't need to take the mass spectrum, or even you don't need to take the UV visible spectrum. Just if you can have the IR spectrum for this region, that is enough to find out the molecule, what is the molecule, what is the structure, what is the name of the molecule. Just like as just thumb. Okay, fingerprint, so you can take it. So a strong peak is tall. Here, this one you can consider, this is very high intense. That means it is absorbing very high. So it has very low transmittance. That means if you consider here, that means if we consider this is the close to 0, that means it is absorbing most of the IR lines. So it has very high intensity. Therefore, what we have mentioned here, a strong peak is very tall. Medium peak is mid height. That means if we consider maybe not here, this is very maybe this one. This one can be just this is very high intense. This is maybe 30 to 40% transmittance. So or 30-40%, what we have mentioned in the slide, 35 to 75%. That is the transmittance. So absorbance will be around 25 to 65. So weak peak is short, transmittance is high. That means in that case we can consider maybe this 2 or here that can be very weak signal or intensity. Okay. What is the difference between UV and IR? UV and IR. In last class we have learned about the UV and today we are learning about IR. Then what is the difference between these two techniques?
I think in movie, the difference is that the max absorb wavelength and here it is only that particular wavelength.
We can say that we also observe the max for IR also, because if we say if we enlarge this signal, if we expand this region only, this region, then you can have somewhere the max. Okay, maybe I can help you. Just in terms of energy, IR is very low energy and UV is quite high energy. And another thing, the major difference between UV and IR spectroscopy is that UV spectroscopy is used to obtain the absorption spectra of a substance, whereas IR spectroscopy is used to obtain the functional group present. This is in terms of use. What types of for why we are going to use the UV and IR, but the major difference are different from the wavelengths. That means how much energy we are applying for UV. That means for molecule, it's going to give you the excitation from ground state to excited state for the UV, and for IR, it is giving the excitation from the one vibrational state to another vibrational state. So,
when you said that IR has a stronger wavelength than UV.
a stronger wavelength, longer wavelength, not as longer wavelength. Okay. Yeah, that is in terms of energy. Yeah, same thing. That is also already mentioned. Right? So today we are going to end here because we do not have more time. We want to take the attendance. And if you have any question, then you are welcome. Any question? Okay, thank you.